to a task, and it trusts that the task is eventually going to yield back to the scheduler. If that doesn't happen, then bad things happen. So you shouldn't do that. And the reason why we did that instead of doing preemption or something is actually so that we can integrate the I/O system into the scheduler to get this non-blocking but still synchronous I/O structure. Tasks have the option of running a cleanup job when they yield to the scheduler, and that's actually how we start the I/O and process all that. And that's going to just be important when I describe how we actually do I/O. The scheduler, before it runs a task, checks with the libuv event loop to see if there's anything that it needs to do, like, say, process a completed read or an incoming connection attempt. And if you want more details, I would suggest going to look at Aaron Todd's A Work Stealing Runtime for Rust presentation a couple weeks ago. It should be on Air Mozilla. So we have cross-platform and non-blocking from libuv, but it's asynchronous, and we want synchronous. So how are we going to handle that? It's actually pretty simple conceptually. It gets a little tricky when you actually try to implement it, and it's a little easy to mess up. But the basic idea is when a task starts to do I/O, it calls read, for example. And the first thing read does, it may do some preparatory stuff of allocating buffers, but basically the first thing that it does is it yields itself to the scheduler, and it blocks itself, basically. And it gives the scheduler this cleanup job that it needs to run before it goes and picks some other task to do. And in this cleanup job, we actually call into libuv and call libuv's read function, which takes some callback. It starts a request, and it takes a callback to run when the request completes. And we actually take the task, and we wrap it inside this callback and basically give it to libuv. And then that's non-blocking, so that call finishes, and the scheduler goes and finds some other work to do somewhere else. And then sometime later, it could be almost instantly, it could be, who knows how long. The I/O request finishes, libuv registers this event in the event loop queue. Eventually, it gets to the top, and the scheduler sees this event happens, and it runs the callback. And this callback gets the output from the event, either like, so if it's a read, it'll get like a buffer that's filled with data, or it'll get like an error that something went wrong. You tried to read from a socket that has been closed on the other end or something. And it also has that task that we blocked. So it processes the output, and then it tells the scheduler, I want you to immediately resume this task that we blocked. So from the task perspective, it calls I/O, and it stops, and nothing happens until the I/O finishes, and then it resumes. So as far as the task is concerned, I/O is synchronous and blocking. But from the scheduler's perspective, we started the I/O and then went and did something else, and then later the I/O finished. And we might have multiple I/O actions overlapping from different tasks. So as far as the scheduler is concerned, we have asynchronous non-blocking I/O. And what this ends up doing is you end up with the ease of programming in synchronous I/O, but you get the performance characteristics of non-blocking I/O. And this is all hidden to the programmer. They just see synchronous, and they get performance of non-blocking. And they don't have to care about any of this. This is just for runtime people. Awesome. So now we have synchronous, cross-platform, non-blocking I/O. What happens when we add multiple threads? Well, we run into problems. Since libuv is single-threaded, when you create a handle or a watcher, it's associated with the event loop you created it on, and it can only do I/O on that event loop. But we don't know that watchers are going to always stay on the event loop they're created on. If a task gets stolen by someone else, it's going to be on a different thread. If a task sends it over a channel to a different task, that could be on another thread, or that task could be stolen. And then that task could be on a different thread and try to do I/O on a watcher, and bad things will happen if you try to do that. You'll probably segfault or just start getting nonsense. And we would really prefer our I/O system to not start randomly segfaulting all over the place. That would not get us very many users. So what a watcher needs to do before you do I/O on it is it needs to make sure that it goes back to its right scheduler, to the home scheduler, and not leave until it's done. But we don't want to just pin a task, any task that could possibly do I/O, onto its home scheduler, because maybe it only does I/O some of the time, and maybe some of the time, and maybe it does a lot of work at other times. We want it to be able to be stolen and get all that nice parallelism. So we can't just pin a task, one, because we want the performance, and two, even if you pin the task, it could still receive watchers from other event loops, and if it tried to do I/O on that, then now you just have nothing to do, because you have to stay on your scheduler, but you can't do I/O on that scheduler, and you need to go somewhere to do I/O, and then what do? You just abort, because there's nothing to do. But we can fix that. So this is actually what really happens when you call read, is there's all this wrapping around the synchronous read call that we just discussed. There's actually this homing I/O wrapping code that works around it. So when we first create a watcher, it has the secret little field that contains a handle to its scheduler. And when you start to do an I/O call, the first thing that it does before it tries to do any I/O is it actually yields the task, and it tells the scheduler, send me to wherever my home is. And maybe this is the same scheduler you're on, maybe it's someone else. And you'll go as a message to that scheduler and sit in the queue. And eventually, you'll get to the front, and you'll wake up on your home scheduler. Awesome, you're on your home scheduler. It's time to do I/O. So you start I/O, and the task blocks. Since the task blocks, you're not going to get moved off until the I/O completes, so you don't have to worry about that. Eventually, the I/O finishes. You're in the event loop. Eventually, you wake up. All right, you're done. Awesome. But as it stands right now, you're now pinned onto the home schedule, onto that scheduler. So if you were stolen and tried to go somewhere else before you executed any code, that scheduler would send you back. And that's not what we want. So we need to go back and yield again and unset this home field of the task so that it can go somewhere else. And this sounds like it might be a little error-prone and kind of tiresome to write out all over the place. But luckily, you don't have to, because we can actually, this is actually all encapsulated for you in a wrapper method. And all you do is you give it a closure that actually does your I/O. And it takes care of all of the scheduling for you. And there's also a variant that gives the I/O action to scheduler that allows the I/O action to perform its own scheduling operations, which is how you then do the blocking I/O. There are other variants that don't need to block the task, which don't need that scheduler. And there's some other variants as well. Any questions so far? There's a lot of stuff, and it's all cumulative. Feel free to interrupt. No? Okay. So this is really only low-level stuff so far. It's all implementation details. And someone who's using I/O in Rust shouldn't have to care about homing I/O and libev event loops and all this. They shouldn't even need to know about it. So, and what this does is then we can later, scrap homing I/O when we can move stuff between event loops. We can use something aside from libev, all this. And the way that we do this is pretty standard, except a little bit for some Rust-specific things. We just use a collection of traits, which is Rust parlance for what a Java programmer would call an interface, or a Haskell programmer would call a type class, to define the I/O operations that we can actually do. And the high-level stuff is just built on top of those traits, and it doesn't know how it's implemented. And the low-level stuff just implements the traits. And then there's like the that just defines the traits and gives you a factory to construct trait objects for the high-level system to use. And it gives us a little bit of overhead because the trait objects use dynamic dispatch when you call things like read ultimately, but it's worth it for the loose coupling that we gain. So now our I/O system is independent of its implementation. It's cross-platform, it's non-blocking, it's
Let me space mute and everything.
but we still need to make it resource safe. And this is all actually at the high level through the type system. And why do we need to do this? Well, resources like file descriptors and sockets and pipes and timers and all this are stateful, and they have operations that are only valid at certain times. And in a lot of APIs, this is true, but it's not actually enforced in any way. If you're in the C-level socket API, you can easily call read before you call bind on a socket, and it doesn't make any sense, and nothing's going to stop you. And in more modern languages, it's a little bit better, but it's still not perfect. But really, we should forbid all of the invalid uses. It should not even be possible to do something that's wrong. And modern languages can get a little bit of the way there. You can do something like if you have a TCP stream, which you can read from, you can only get that by accepting an incoming connection from a listener or by successfully making a connect call. So you can't read from an unconnected socket, basically, which is good. Great, okay. But then there's other stuff that it can't do. Like it can't require you to close a socket before you free it. It can't, or another example here is if you have a listener, you have basically three ways you could structure it. Either it starts listening when you create it. It starts listening the first time you try to accept something. Or there's an explicit method you have to call to start listening. Is something happening over there? Okay. All right. Or exposes a particular listen method that you have to call explicitly. And if it starts listening when you create it, that gives you a little less control, which it's acceptable, but it'd be better if we could control it. If it starts when you first call accept, then you run into a problem if you can't actually, if you're writing multi-threaded tests, you can't actually establish that the server has started before you have like a client task try to connect to it, which just ends up becoming annoying because you have to write all this other code to do it. Or you can expose a listen method that starts a listener, but you end up with the problem of what happens if you call listen when you're already listening? You shouldn't be able to start a listener when you've already started the listener. That doesn't make any sense. That shouldn't even be possible. But you can't do that with type systems in Java because you can't model consumption. But linear types, which Rust has, let you model consumption. A linear type is basically a type that ceases, if something has a linear type and you use it, you don't have it anymore. It's gone. You can't make copies of it, really. Some things are copyable, but not everything. Unlike in regular type systems where if you have an integer, you can make infinity copies of the integer. In a linear type system, if you have an integer, that's it. If you use the integer, it's gone. So Rust has a variant of linear types called affine types, which actually means you can either use it once or not use it. And basically what this lets you do is it lets you write functions that require the caller to give up ownership of an argument to the function. And then the caller will no longer have that, and they can't use it again. So for example, if the argument's not copyable, if it was copyable, then you can, if it's copyable, like an integer is copyable if it's on the stack, then you can, make as many copies as you want and call the function as many times as you want. But if it's not copyable, like say a unique pointer, obviously unique pointer is not copyable because otherwise it wouldn't be unique. So if you call a function that takes a unique pointer, you lose that pointer, and now the function has it. You can't call the function again because you don't have a unique pointer anymore. So the way that you do this to make APIs that kind of encode this kind of state consumption property, for example, is if you have a listener, it doesn't start listening until you call listen. But when you call listen, it consumes the listener, and you don't have the listener anymore. And instead what you get is an acceptor, which gives you an accept method, which waits for an incoming connection. Or actually, it also lets you create an iterator over incoming connections. So then Rust has a for loop protocol that works on iterators. So you do like for x in iterator, and you have a body, and it will just go over that iterator until the iterator is exhausted and process each element in there. Since incoming connections are an infinite stream, you can basically just process all of your incoming connections for forever if you wrote a basic web server by doing for stream in acceptor.incoming, and then you have a body, and that's it. But what this makes is it makes it impossible to accept before the listener starts, and it makes it impossible to start listening twice. It's just if you try to do that, the type checker will yell at you until you stop trying to do that. Another good example, most resources require that you close them. You have to close a file. You have to close a socket. If you don't, then you'll slowly exhaust the file descriptors of your operating system until eventually you don't have any anymore. And that would be bad. So the way that we do this is we override the destructor for these IO handle objects. And the destructor is going to run exactly once, and it's going to call close. So it makes it impossible to not close a resource because the destructor is always hack to get working until we actually build the thing. We run into a problem repeatedly since Rust is dogfooding everything. But the Rust compiler is written in Rust. The Rust runtime is written in Rust. And we're using that to further write Rust. So we run into a lot of problems of, we really need this feature, but it doesn't exist yet because we haven't implemented it. And we need to implement it before we can implement it. So like we have to do this temporary hack to like get it part way and then complete the circle. I think people have done some work of running Rust without the runtime at all. It's called 0.rs, and just running it on bare metal. And it's been, I don't think it always segfaults now. But it's conceivable that we could get on the mobile eventually. Like I know Haskell actually recently just figured out how to compile to iOS. And conceivably Rust could do something similar eventually. Yeah. Then you wouldn't be stuck with Objective-C anymore. Or Java. Any other questions? No? All right. Okay. Well, thank you. And I guess we're done.